Hello, physics students, and welcome to this screencast by yours truly, Mr. Welch. This screencast, like I said, is just going to continue on from lecture on Monday. So we briefly got into the idea of the conservation of energy, and really we actually used the conservation of energy in two of the scenarios. Yesterday we did it in the exercise ball slingshot, and we also did it in the Wile E. Coyote example, and that's where I really got into the idea that conservation of energy is a thing that we really have to worry about. So I gave you the definition. Energy can neither be created or destroyed, only transferred and or transformed. You know, in that first part, energy can neither be created or destroyed. Really what that's saying is that energy is constant. Okay, it's constant. And I'm writing with my finger on this screencast. I forgot my stylus, so I apologize for any bad handwriting. So that first part really just means that the amount of energy is constant. But the thing that can fluctuate is what type of energy we have before an event or after an event. So within the idea of conservation of energy, we can start talking about this idea of total mechanical energy. Now, we've talked about mechanical energy. We know we have three types. You know, we have potential, gravitational potential energy, we have elastic potential energy, and we have kinetic energy. Those are our three types of mechanical energy. But now, the total mechanical energy is the sum of all the types of mechanical energy an object possesses. So we can write like a little equation for this, and we can say that ET, or energy, total mechanical energy, is equal to the gravitational potential an object has, the elastic potential an object has, and the KE, or the kinetic energy an object has. Now, an object could have all three of these, it could have two of these, or it could just have one of these types, okay? So this is the full equation, but sometimes you might just have gravitational potential, or sometimes you might have a combination of all three. Okay, so going off of that a little bit further, we actually have an equation for, or an expression for, conservation of energy. And so we can say that the energy, or the total mechanical energy before, or the initial total mechanical energy, has to be equal to the total mechanical energy after, okay, or the final. Now, I keep saying before and after, and again, I'm just going to reiterate that that's before or after some event. So yesterday we had Wile E. Coyote jumping off the cliff. Well, the event would be him jumping off the cliff, okay? So before, all he had was potential energy, and then after that event, you know, his potential energy was being converted into kinetic energy. So let's just take a look at that in a simple example. We'll just go back to the exercise ball slingshot we had from class. Now, if I remember correctly, we had a stored energy, or our slingshot energy was 964.8 joules. Okay, so we would then say that our mechanical energy total initially was equal to that very value. Okay, so it was just that. So that was the initial total mechanical energy in that system. Okay, but now what happened? Well, they released the slingshot. That elastic potential went away, but it had to go somewhere, right? So it got converted and also transferred into the ball as kinetic energy. Okay, so what we said yesterday was then that our KE was equal to 964.8 joules. What is that KE, though? We can consider that KE to have been our total mechanical energy final in that system. Okay, after the event of the slingshot being released, this was our total mechanical energy final. All right, I hope that makes sense. But as you can see, you know, these two numbers here, they have to equal each other because we define that up here. Okay, energy, total mechanical energy before has to equal total mechanical energy after an event. Just to reiterate this even further, I want to look at an example that's pretty similar to the Wile E. Coyote example. So I have a picture here. It's actually not a bad drawing of a guy. He's doing some doing some diving off of what looks like a tower into a swimming pool. Okay, so if we take this and we say that our zero level is the top of the pool here, well, we can see that at the top here, this guy only has potential energy, right? He's not moving, so let's just say that he has a PE of, I don't know, 5,000 joules. So what does that mean then? Okay, before this event, before he jumps, what is this potential energy? This is actually our total mechanical energy before. Okay, so this is the total mechanical energy of the system. It cannot have any more energy than this 5,000 joules. All right, so now he jumps. Okay, he jumps. And when he's halfway down, which is right here, we know that he's moving, but he's also some distance above our 0 point, correct? So what can we say here? Well, we would say that he still has potential energy, and he actually has half of the potential energy that he had initially. So he has 2,500 joules of energy. But now he's moving. But we're still missing, 2,500 joules, because this, we said, was the most energy that we could have. This is our total energy. So where did that energy go? Well, it got converted into kinetic energy. So he has 2,500 joules of kinetic energy. Okay? So what does that mean? Well, that means that our total mechanical energy is still equal to 5,000 joules, right? Because 2,500 plus 2,500 is 5,000 joules. So I want to take this another step, and I want to figure out, what the energy is here at the 0 point. Well, if he's at the 0 point, there's no height, right? So we can just automatically say that our potential energy is 0 joules. What about our KE? Our KE, well, we don't even have to know. We don't even have to know how fast he's going, because we know in our system, that we have to have 5,000 joules of energy. We just have to. That's what the conservation of energy tells us. So we can know right away that we need 5,000 joules of kinetic energy. And lo and behold, what does 5,000 plus 0 joules equal? Well, it equals 5,000 joules. And that was our total mechanical energy for this scenario. We could take this even another step further, and we could figure out what the kinetic energy and the potential energy is after falling 1/4 of the distance and also 3/4 of the distance. I'm not going to do that in this screencast, but basically what you have to think about is, what's the only thing changing? The only thing changing is the height. So if you can figure out what the potential energy is at each point, then you can find out what the kinetic energy is. Okay? Because we know that both the kinetic energy and the potential energy have to sum up to this 5,000 joules. Okay, it has to sum up to the 5,000 joules. So basically, in summary, the conservation of energy tells us that the energy in a system has to be constant. Okay, but the energy within that system, it can be converted to different types. Okay, and then we really kind of define that based on an event that happens. So in this scenario, the event was the guy jumping off of the platform here. Okay, so before he jumped off, all he had was potential energy. But then after that event, what happened? Well, his energy got converted from potential into kinetic, and then here it just got converted all into kinetic. So just remember with the conservation of energy that in a system the energy is constant, but that energy can transform and it can be transferred among objects. I hope this screencast was helpful, and this will be very useful. This information will be very useful with the activity that we do on Thursday. Take care, physics students.